series of this common emitter amplifier. So in this video, we will actually see uh, the justification of various biasing techniques and how do we say the stability of the biasing will improve from fixed bias to voltage divider and then voltage divider to emitter degeneration resistance. So we'll do that. Uh, Again, okay, we will also see the actual amplification of a small signal for which these are the basics you should be knowing. Okay, with this background, okay, what I actually did here is so took this circuit, took VCC is equal to okay as we did in the previous example. I took the same values of RC, RB, RC, R1, R2, RC, R1, R2, RE. So what I did here is so because I want to see whether this circuit with the potential divider with emitter degeneration is most stable among all of them. So what I did here is, so I took each of the circuit, I varied the value of beta from 100 to 110 and 90. I just intentionally made the value of beta factor 90, 100 and 110. And here also I made it okay once it is 90, once it is 100 and once it is 110. So then calculated or obtain the values of the collector current. So that's what is listed here. uh, Taking this as the basis or the reference current or the value of beta with beta as 100. So in this fixed bias I got a collector current of 1 milliampere. When I vary the value of beta from 100 to 110, the current increased to 1.11 milliampere. So there is a 11% change. And when I reduce it to 90 from 100, so it has resulted in a current of 0.901 milliampere. So there is a 9.9% change as the value of beta changes. So meaning you cannot overcome the variation of beta onto the variation of your IC. So this is reflecting over here. So then I just took this circuit again, did the same thing. So with beta as 100, the current happens to be 1.03, taking this as the reference current. When I vary the value of beta to 110, it has become 1.11, again 11% variation. There is no much difference in the variation of your AB, the IC. Again 11% change for a 10% change in your beta value, so which is bad. So again, the improvement of this potential divider circuit is you have a specific voltage which is not a floating voltage. So you have a potential voltage exactly here, but here it will be a floating one. And again, when it reduced to 90, so there is a reduction of 7.7%. Again, this is not a appreciable stability in terms of change in the IC. So IC changes along with your beta. Then we did the same thing for potential divider with emitter degeneration. It is very interesting to see when this was when beta was 100. Here had it as 1.01. When beta increased to 110, the increment of this IC is hardly 4.95%. In the previous two cases, there was a 11% increment. Now you can see the increment is less. So as the value of beta changes, the change in IC is not that much. So it is a better stable in terms of biasing circuit. So with potential divider with emitter degeneration. When I change the value of beta from 100 to 90, there's a 10% reduction, but this is reduced by hardly 3.96%. So this is still a better performance. So among all these divider biasing circuit, which is a fixed bias, potential divider, and potential divider with emitter degeneration, potential divider with emitter degeneration is the best biasing circuit having good stability over the changes in the beta value. So this is intentionally varied, but you are still having the same current. Usually we will not change intentionally because of some temperature changes. If your beta changes, then your IC still remains the same. So that's what is the analysis of biasing of a circuit, of a BJT circuit, using potential divider and emitter degeneration resistance. Okay, let us proceed with the design or amplification of small AC signal using RC coupled amplifier or CE amplifier in general. So that is so here let me write the circuit here. So this is where I take the output voltage we know. Here where I measure the DC voltage. This is VCC. Here this is the coupling capacitor which couples the AC signal to the amplifier circuit, called as CC. This is the small input voltage. This is R1, R2, RC. So we can write the equivalent circuit of this as something like this. So now, okay, now we have the DC equivalent circuit would be this. So let us take the same values of R1, R2, RC as we obtained in the previous case for a Q point of 1 milliampere and 2.5 volt as your DC, so which resulted in a value of R1, R2, and this is supposed to be 2.5 kilo ohm. This is VCC equal to 5 volt, and let me just go back and see what is the value of RC. Let me just check it here only. I think this is the value 53 kilo. Let me just take out this. Okay, let me save it. Okay, this is the value what we're talking about. It is 53.3 kilo ohm, and this is 12.309 kilo ohm. This has 2.5 k, and this is let me add a capacitor here. Let's rotate it. So this is the capacitor, and then let me get a voltage source. This is the voltage source. Let me name it as Vin. This is Vin. Here let me measure output voltage here. It as out. Let me connect. So since I want to do, let me have this as 0.1 microfarad. Let me just take hardly 10 millivolt as the signal. Let me also change. Okay, that is not DC. Let me go to this advanced. So let me use the sine wave. Let this be 10 millivolt. Let the frequency be around 20 kilohertz. And okay, that's it. So now let me do the transient analysis. So let me do transient analysis. Since it is 20, okay, this has become 2k. Okay, let the timing be fine. Let me take it as 20k. This is 20k. Let me run this. So I have this as my input voltage, input sine wave. You can see 10 volt peak and minus 10 volt here, and this is the output voltage which is over here. Let me separate them. When I separate it out, let me add a pin above, and let me take the output here. This is output and this input. If you see very few cycles, so what I'll do, I'll just zoom this portion. See, now this is output. What I do is, let me introduce some delay. let me introduce a delay of where is that delay? So delay is here. Let me introduce a delay of maybe zero point 0.1 millisecond. Let me see the difference here. Okay, let me show you what is this. See, here I don't have the signal, so the input is 0, but you can see still you have the output. So what is output? So output that you have without input is this. This is what it is. How much is that? That is 4.41. So that is the DC voltage at this point without input. So without input, I have a DC voltage of 2.41. So let me write that VC as 2.41 volt. And once you apply the input, which is increasing like this, you can see the output is reducing. If you measure the peak to peak of input, you know that input peak is 10 millivolt and here it is minus 10 millivolt. So peak to peak input is 20 millivolt, meaning if I write what is V in peak to peak is actually 20 millivolt. So what is V naught peak to peak? Let me measure. So this is VC 2.41 volt that I measured. Here's the DC voltage. What is output peak to peak? Output peak to peak, let me just double click on this and measure the peak to peak voltages, for which I should keep one at the top, one at the peak of this and other one at the minimum. Okay, that is peak to peak, which is 1 point. So okay, let me just put this up here, put this down. Let me make this down here. This is okay. Let me further zoom this. Okay, let me go to the minimum possible. This is minimum, that is maximum. Can you see it is 1 point? This is 1.27. That is, this is 1.27 and this is 3.27. So the difference is 1 point. This is the vertical difference. Vertical difference is, so V naught peak to peak is 1.99 volt. This is what is uh, the gain. So the output voltage peak to peak. So this is output voltage peak to peak. This is input voltage peak to peak. So then what is gain of the amplifier? Gain of the amplifier is output by input. So since I measured peak to peak, output peak to peak by input peak to peak, which is nothing but 1.99 volt by 20 millivolt. So what is 1.99 by 20 millivolt? So it happens to be 1.99 divided by 20 exponential of minus 3. You can see now it is gain of the amplifier, which we write it as AB is equal to 99.5. This is the gain of the, this is the magnitude of the gain of the amplifier. So whatever input that you applied here, that is amplified by 99.5 times, almost 100 times it is amplified. So that's what is the indication of this. If you can see here, let me go back to the circuit. See now, you cannot make out whether it is 100 times increase. Only when you merge them together, when you are just making them together, now you can make out. So what I'll do, I'll take out this pane. How do I delete this pane? Okay, I have deleted. Now you can see. Okay, I will, now you can see this is your output. Input is so small. So now you can make out this is 100 times. The output is 100 times that of the input. When you're separating it out, almost both of them looks similar because this is zoomed out. This is zoomed out. So now uh, that's what is the gain. So gain is almost 99.5. But how to theoretically verify that the gain is 99.5? And it is one more interesting thing to see here is that if I just put it in different pane, I will add a pane below this. I will take this signal down. Take the signal down. Can you see? If you just zoom this out, can you see this is your input voltage increasing but the output is reducing. When the input is reducing, output is increasing. So it's actually out of phase by 180 degree. So that is represented in your gain expression by negative sign. So this is actually minus. This is minus 99.5. So if you're applying a signal something like this, it is amplified by 95 or 99 times in reverse direction. In reverse direction, this is how it is happening. Let us see the how we got it as 99.5 as a gain. So let me because now which signal you are amplifying? You are amplifying a small signal. So let us write the small signal equivalent circuit of this whole amplifier circuit. So now for small signal analysis. In small signal analysis, I will again rewrite the same circuit. I will rewrite the same circuit. I will rewrite the same circuit. This is VCC, this is ground, this is R1, R2, RC. Fine. So this is V in, this is your V out. So now in small signal analysis, I will consider this as ground. So it is now replaced by ground. Once this is ground, this is also ground. I can merge these two together. So this will become something like this. So this is R1, R2 parallel. You are having this input voltage, and this is your base. This is this, and this is also. You can see all DC voltages are grounded. One DC voltage is grounded, so that DC is grounded here. So this emit collector is connected to the RC. This is your collector connected to RC. This RC is grounded. This is RC. This is grounded, and this is CC. So this is VN. So for small signal AC signal, this is also considered as a short. This is also considered as short. So now this further reduces to this R1 parallel R2, and this is your small signal. This is your V0 R1 R2. This is V in. This is RC. This transistor is further replaced by something like this. So you have R1 R2 and this is your V in. This transistor is now replaced by this is base emitter collector. Between base and emitter you have a resistor R pi. Between collector and emitter you have a current source which is Gm into V pi. So that V pi is actually this voltage, and you have this is your RC. You can see now this transistor is now replaced by this. So what is this transistor replaced by? This transistor is now replaced by this is base collector emitter. Between base and emitter it is replaced by R pi, and between collector and emitter it is replaced by a current source which is equal to Gm into V pi. So V pi is the voltage across base and emitter. V pi you can treat it as VBE or the input voltage that is applied. So this is your V. This is your V. You can see it as V. So this is your equivalent circuit. So now how much is so what you have? You have a equivalent circuit something like this. This is R1, R2 parallel. This is R pi. You have a current source which is Gm into V pi, and this is V0 which is RC. This is R pi. This is R1. This is R2. Let me ground it. This is V. So what is V0? I can say if you say this is I0, can I say V0 is equal to I0 into RC? This I0 is nothing but Gm times V pi is nothing but V in. Gm times V in So actually this I naught is in this direction, whether this gm into v pi is in the opposite direction, this becomes minus of gm into v into rc. So this is v naught. So what is v naught by v in? It's actually now minus gm into rc. So as you know, in the earlier videos we said that gm is equal to ic by vt. So how much is ic? It is 1 milliampere and vt is 26 millivolt. How much is this now? Minus of uh, 1 milli by 26 millivolt is your gm multiplied by rc is how much? 2.5 kilo. If you substitute all these things, so this is your av gain, voltage gain. What is voltage gain now? So it is that. So what is gm? So gm is almost 1 over 26. So minus of 1 over 26, and this is 2.5 k. So it is now 2.5 exponential of 3 divided by 26. Can you see the gain is 96.15 minus is your v naught by v in. So your gain upon calculation is coming out to be 90. Of course, maybe IC slightly more. If you just go back to this and try to find out how much is IC, how much is IC here. What I do is let me go back to this. Okay, I will minimize this. Let me add a current here. Add trace. How to add trace? You can add traces corresponding to IC. Okay, let me measure current IC and then add here. If you can see what is IC, okay, let me just go here and measure here. How much is IC? Okay, let me just measure the current corresponding to how I measure IC. 1 second. Let me go back to this. Where is that? Sorry. Let me go back to this and do a dot OP of this. When you do a dot OP of this, this is dot OP. Okay, now you run. How much is IC? IC is actually 1.03. Suppose if I replace this by 1.03 milliampere, can you see it is 1.03? This is the small modification. The current is 1.03, so it is 1.03 divided by 26 into 2.5 exponential. Can you see it is 99.5? 99.03 is the gain. How much the gain we got? So this is 96. If I take it as 1 milliampere, actually current is 1.03. So how much the gain? Can you see the gain is minus 99.03 milliamp? Sorry, volt per volt in your calculation. So in calculation also gain is minus 99. In your simulation also we got the same gain. So this is how we can able to find the expression for gain for an amplifier. This is theoretical value of gain, which is actually found in simulation also. So this is the expression for gain. So AV, which is gain, is given by minus GM into RC, where GM is IC by VT into RC. So if you change IC or RC, the gain will change. The gain will change. So this is how you can able to design an amplifier of desired frequency, of desired gain. Suppose you want to have a gain of 50, I can get a gain of 50. So assume that GM is equal to IC by VT. Let me not change the value of IC. Let it be 1.03 milliampere and let this be VT, which is 26 millivolts. How much is the gain? So gain I want to have it as minus 50 is equal to minus IC by VT into RC. So how much is this? Minus 50 minus 1.03 milliampere by 26 millivolt into RC. Let me find out what is RC. This minus and minus will go off. It is 50 alpha equals 1.03 divided by 26 into alpha A shift can. RC is equal to 1.26 kilo ohm. I will get a gain of minus 50. Okay, I will change this resistance to 1.26. I will change this to 1.26. 1.26. 1.26 as my RC value. 1.626k. If I save it and then if I do again dot trend, if I do dot trend and then run, if I measure the output peak to peak, if I measure the output peak to peak, input peak to peak or 20 millivolt. Let me measure output peak to peak. Let me just zoom it out. This is minimum. Let me keep this at maximum. How much is the vertical difference? It is 999 millivolt. So V naught peak to peak is 994 millivolt. How much is V in peak to peak? That is 20 millivolt. So what is 992, sorry, 994 divided by 20? Yes, actually you can see 49.7 volt per volt. This is 80. You can see now we actually designed for a gain of 50. We actually designed for a gain of 50 here. So if you change the value of RC to 1.26k, you're getting a gain of almost minus 50. You expected minus 50, you're getting minus 49.7. So this way you can able to design an amplifier for any gain. Thank you.